Okay, so we've covered a lot about the universe, but today let's dive into one of the most extreme, mind-bending objects out there, black holes. We know they're super dense, gravitationally powerful, with a point of no return. But what is that point, and what happens when you cross it? Einstein's general relativity tells us gravity isn't a force, it's the curvature of space-time. Black holes are the ultimate space-time warpers, bending space so dramatically that nothing, not even light, can escape. Their defining feature is the event horizon. Imagine this. Refer to Figure 1. A star collapses, distorting space-time. As an astronaut, you'd be stretched and squeezed, spaghettification. The event horizon constantly recedes at light speed, making escape impossible. This horizon isn't a physical surface, but a boundary. Refer to Figure 2. The thick black vertical line marks the event horizon. Red lines are ingoing light, blue are outgoing. Notice how inside the horizon, outgoing light, blue lines, fails to escape? It's trapped, heading to the singularity. Green light cones show all future paths point inwards. No escape. It's a terminal instant. How does it form? Refer to Figure 4. As a star collapses, early light fronts, green, escape. But later ones, red, are dragged back so strongly by gravity they collapse inwards. That dividing line, the light ray separatrix, is the event horizon. Refer to Figure 6. This diagram shows the event horizon is the boundary, and the black hole is the causally disconnected region it encloses. No signal from inside can reach us. We've even seen horizons merge. Refer to Figure 7D. When two black holes collide, their horizons fuse, forming a pair of pants made of light rays. The implications are profound. Roger Penrose proved that if gravity is strong enough to make even outgoing light fronts contract, a trapped surface, then a singularity is inevitable. Refer to Figure 8. This image shows light. Normally, it expands, but under extreme gravity, it might not, apparent horizon, or even contract. Penrose's theorem states if such surfaces appear, a singularity will form. What about light around a black hole? Refer to Figure 10. Light can orbit at 3 times the black hole's mass, the photon ring. These are unstable orbits, like balancing a ball on a hilltop. Light spirals in or escape. This feature is crucial for imaging black holes like M87. Black holes aren't static. Disturb them and they vibrate. Think of a damped bell. These are quasi-normal modes. Refer to Figure 12. Waves hit an effective potential barrier around the black hole. The most dominant vibrations are concentrated near the photon ring at 3M. They're like waves in a leaky box, slowly radiating gravitational energy. This ringing tells us about the black hole's mass and spin. Most black holes rotate. This leads to frame dragging, where space-time itself gets pulled into a whirlpool. Refer to Figure 13. The horizon is dragged along. This creates the ergosphere. Refer to Figure 14, an oblate sphere outside the event horizon. Inside, the dragging is so intense you must move with the black hole's rotation. You can escape, but not stand still. The ergosphere enables the Penrose process. Refer to Figure 15. A particle enters, splits. One fragment has negative energy relative to a distant observer and falls in. The other escapes with more energy than the original. This extracts rotational energy, spinning the black hole down. This also happens with waves, called superradiance. Refer to Figure 16. A wave hitting a rotating black hole gets amplified. If a mirror barrier exists, the amplified wave bounces back, creating a black hole bomb that drains the spin. This could help detect ultralight scalar fields. Finally, quantum mechanics. Stephen Hawking discovered black holes aren't truly black, they glow. They emit Hawking radiation. Quantum fields constantly create virtual particle-antiparticle pairs. Near the horizon, refer to Figure 17, one particle of a pair falls in, negative energy, while its partner escapes as a real particle, positive energy. Energy comes from the black hole, so black holes evaporate. It's incredibly slow. A solar mass black hole is colder than the cosmic background radiation, taking quadrillions of times the universe's age to evaporate. Its surface area is also its entropy, an immense measure of internal microstates. But if a black hole evaporates, what happens to the information that fell in? This is the black hole information loss paradox. If a book falls in and the black hole disappears into generic thermal radiation, is the book's information gone forever? This conflicts with quantum mechanics, which states information is always preserved. The paradox remains unresolved, but this creative confusion has profoundly shaped our understanding of gravity and quantum information. Black holes, the simplest macroscopic objects, yet the most complex quantum puzzles. They're truly the ultimate drama queens of the cosmos. Thanks for watching, and we'll see you next time on Signal and Theorem.